Find the volume of the solid bounded below by the circular paraboloid z equals x squared plus y squared, and above by the circular paraboloid z equals 5 minus x squared minus y squared. We will determine the volume using a triple integral, where the volume of a 3D region R is given by the triple integral shown here. Before we set up this triple integral, let's look at this in 3 dimensions. Notice one paraboloid opens up, the other opens down. Our goal is to find the volume bounded by these two paraboloids, which would be the volume of this solid here. If we look down on the xy plane, we can see the intersection of these two paraboloids is a circle, and because of this, we will set up the triple integral using cylindrical coordinates, not rectangular coordinates. It'll also be helpful to graph the circle in the xy plane to help determine the limits of integration. So going back to our work, let's first determine the equation of the circle of intersection projected onto the xy plane. To do this, we use the two equations, and let's substitute x squared plus y squared for z in the second equation. This gives us x squared plus y squared equals 5 minus x squared minus y squared. Let's add x squared and add y squared to both sides of the equation, which gives us 2x squared plus 2y squared equals 5. Divide both sides by 2, gives us x squared plus y squared equals 5 halves. We should recognize this is a circle centered at the origin where r squared is equal to 5 halves. So if r squared is equal to 5 halves, the circle has a radius of square root 5 halves, which I've already graphed here, but let's label this r equals the square root of 5 halves. So the volume V is equal to the triple integral over the 3D region R differential V. And again, because the intersection of the two paraboloids is a circle, we will be using cylindrical coordinates where dv is equal to r dz dr d theta. So this is equal to the triple integral, and then we have r dz dr d theta. And now let's work on determining the limits of integration. Notice how we first integrate with respect to z, and the solid is bounded below by the paraboloid opening up and above by the paraboloid opening down. But remember, we need to express the limits of integration for z in terms of r and theta. For the lower limit of integration, we know the paraboloid opening up is z equals x squared plus y squared. We need to express z in terms of r and theta. And remember, when using cylindrical coordinates, r squared is equal to x squared plus y squared. And if you need a review on cylindrical coordinates, you may want to pause the video here and review these notes. But because we know r squared is equal to x squared plus y squared, we can write this equation as z equals r squared, which gives us the lower limit of integration. And then for the upper limit of integration, which is determined by z equals 5 minus x squared minus y squared, which we can write as 5 minus the quantity x squared plus y squared. We know this is equal to 5 minus r squared. The limits of integration for z are from r squared to 5 minus r squared. And now for the limits of integration for r and theta, we will use the intersection of the two paraboloids projected onto the xy plane, which is this circle here. The limits of integration for r are going to be from 0 to the square root of 5 halves. The limits of integration for theta are going to be all the way around the circle, which is from 0 to 2 pi. So this triple integral will give us the volume of the three-dimensional region bounded by these two paraboloids. We first integrate with respect to z. The antiderivative of r with respect to z is going to be r times z. The limits of integration are from r squared to 5 minus r squared. Let's continue on the next slide. When determining big F of b minus big F of a here, remember we substitute the limits of integration for z, not r. which gives us r times the quantity 5 minus r squared minus r squared. Simplifying inside the parentheses here, we have 5 minus r squared, which gives us 5 minus 2r squared. And then we distribute r, which gives us 5r minus 2r cubed. And now we integrate with respect to r. The antiderivative is 5 times r squared divided by 2, or 5 halves r squared, minus 2 times r to the fourth divided by 4, which simplifies to 1/2 r to the fourth. And now we find big F of b minus big F of a. The square of the square root of 5 halves is 5 halves. So here we have 5 halves times 5 halves minus 1/2. When we raise the square root of 5 halves to the fourth power, we get 5 halves squared. And then when r is 0, both terms are 0. Simplifying here, we have 25 fourths minus 1/2 times 25 fourths, which is 25 eighths, which is equal to 25 eighths. We have the integral from 0 to 2 pi of 25 eighths d theta. Let's continue on the next slide. The antiderivative is 25 eighths theta. Which is equal to 25 eighths times 2 pi minus 0, which is just 25 eighths times 2 pi. Simplifying, it's 1, 2, and 2, and 4 2s and 8. The exact volume is 25 fourths pi, and because it's volume, this would be cubic units. So this is the exact volume of the solid bounded by these two paraboloids. Looking back at the homework though, notice how there's already a pi here, so we only enter 25 fourths. I hope you found this helpful.